Welcome back to our course on system engineering. We're going to be, in this chapter, we're going to be focusing on software system engineering. And so some of you may have some background in writing code. Software engineering is another level above that, maybe thinking on thinking about being as an architect, if you will, and also getting into specifics of what would be online with the kind of things that we're talking about in system engineering in general. This is a complicated topic. I teach a whole course on software engineering. So let's just give this a context. So we talked about our foundations. We talked about concept development. Now we're going through these different phases in the engineering development. And so this is now the second of a handful of chapters that we'll be talking about for this. Well, let's start by thinking about software engineering versus software systems engineering. And so thus we have this software perspective versus a system engineering perspective. So information technology is a driving element to what many have called the information revolution, changing the face of modern industry, commerce, finance, education, and entertainment. In fact, the very way of how we live our lives. So IT has accomplished this feat largely by automating tasks that have been performed by human beings, doing more complex operations that have been possible, and doing them faster with greater precision. Not only has this capability given rise to a whole range of new complex software-controlled systems, but it has even been embedded in nearly every form of vehicle and appliance, and even in children's toys. So in other lectures and other chapters, we've discussed the application of system engineering principles and practices to many types of systems and system elements without regard to whether they were implemented in hardware or software. Software engineering, however, has advanced along a separate path than system engineering, and the two paths have not converged. Many principal techniques and tools are similar for both fields, and research has fostered the evolving merger. So the term software system engineering was proposed by Dr. Winston Royal, father of the waterfall chart, early in the history of software engineering to represent the natural relationship between the two. However, the term was not adopted by the growing software community, and the term software engineering became the moniker of the field. Within the first decade of the 21st century, the fact that the two fields have more in common was recognized by both communities, and the old term was resurrected to represent the application of system engineering principles and techniques to software development. Of course, the flow of ideas has gone in both directions, spawning new concepts and system engineering as well. Object-oriented system engineering being one example. Today, the expanding role of software in modern complex systems is undeniable. The two terms, software engineering and software systems engineering, are not synonymous. However, the former refers to the development and delivery of software products, standalone or embedded. The latter refers to the system's application of principles to the software engineering discipline. So accordingly, in this lecture and the chapter that's related to it, we'll focus on software systems engineering and how software engineering relates to systems. In other words, we'll take the perspective of using software to implement requirements, functionality, and behaviors of larger systems. This excludes standalone commercial applications in our discussions, such as the ubiquitous office productivity products we are familiar with today. While system engineering principles could certainly be applied to the development of these types of products, we do not address these challenges. So let's begin to think about the components of software. We define software by its three primary components. Instructions refers to a computer program or simply code. Software includes a list of instructions that are executed by a variety of hardware platforms to provide useful features, functionality, and performance. The instructions vary in level of detail, syntax, and language. Data structures, along with the set of instructions, are the definition of the data structures that will be stored for manipulation and transformation by the instructions. And then we have documentation, which the software includes the necessary documents that describe the use and operation of the software. Next, we'll talk about coping with complexity and abstraction. One of the most fundamental differences between engineering software and engineering hardware is the abstract nature of software. Since modern systems are dependent on the software for many critical functions, it's appropriate to focus on the unique challenges of engineering the software components of complex systems and to provide an overview of the fundamentals of software engineering of most interest to systems engineers. In another chapter and lecture relating to that, we will discuss the relationships between the system engineer and design or specialty engineers. Typically, the system engineer acts in the role of a lead engineer responsible for the technical aspects of the system development. Concurrently, the system engineer works with the program manager to ensure the proper programmatic aspects of system development. Together, the two work hand in hand, resulting in successful programs. Design engineers usually work for the system engineer in the split between responsibilities. So let's get into the software system engineering process. One perspective that can be taken with respect to software engineering is that the software engineer is simply another design engineer responsible for a portion of the system's functionality. As functions are allocated to software, the software engineer is called upon to implement those functions and behaviors in software code. In this role, the software engineer sits alongside his peers in the engineering departments, developing subsystems and components using programming code as his tool rather than physical devices and parts. So in this figure that we're showing here, it's an IEEE software system engineering process chart that depicts the perspective using the traditional V that we are getting familiar with as we're studying systems engineering. Once a subsystem has been allocated for software development, a subprocess of development software requirements, architecture, and design commences. A combination of system engineering and software engineering steps occurs before the software components are integrated into an overall system. Often the time and level of effort in developing software lead to software systems being more complex than other system elements. Unfortunately, this perspective tends to promote independence between the systems and software development teams. After design, hardware engineers and software engineers begin their respective developments. However, the nature of software requires that the software development strategies be devised early during system design, depicted as the second major step in the V. If hardware and software are split during the design phase, and during or at the end of the system design, then the differences in processes developing and implementing these components will cause the system development effort to become unbalanced in time. Therefore, the software development must be integrated early in the system analysis phase. Although not shown in the figure, system architecting is now a major portion of what the process constitutes as system analysis. It is during this activity that software system engineering is considered. Well, let's talk about the role of software and systems, and we'll also get to this chart talking about the software hierarchy. The development of software has coincided with the evolution of digital computing, which in turn has been driven by the growth of the semiconductor industry. Software is a control and processing element of data systems. It is the means by which a digital computer is directed to operate on sources of data to convert the data into useful information or action. Software controls computers ranging from single chips to tremendously powerful supercomputers to perform an almost infinite variety of tasks. The versatility and potential power make software an indispensable ingredient of modern systems. Simple and complex, software provides the interconnections to many system elements. While software and computer hardware are intrinsically linked, the histories of their development have been very different. Computers tend to be standardized in design and operation. All the processing requirements of specific applications are therefore incorporated into software. This division of function has made it possible to put great effort into increasing the speed and capability of computers while maintaining standardization and keeping computer costs low by mass production and marketing. Meanwhile, to handle the increasing demands, software has grown in size and complexity, becoming a dominant part of the majority of complex systems. So a traditional view of the role of software in a computer system is represented in this figure. The figure shows the layering of software and its relationship to the user and to the machine on which it runs. The user can be either a human operator or another computer. The user is seen to interact with all layers through a variety of interfaces. The user interface is wrapped around all of the software layers, as well as having some minimal interactions directly with the hardware. Software at the application level is the essence of the computer system, and it is the application that is supported by all the other layers. So we'll get into a three-tier architecture. So modern software systems are rarely found within single standalone computers, such as that represented in the previous figure that we were just showing here, and those types of interfaces. Today, software is found across complex networks of routers, servers, and clients, all within a multi-tiered architecture of system. So the figure we're showing here depicts a simplified three-tier architecture utilizing thin clients over a series of networks. Within each component of the architecture, a similar hierarchy as depicted in the previous figure is resident. The complexity of computer systems has grown significantly. Software is no longer dedicated to single platforms or even platform types, but must operate across a heterogeneous hardware platforms. Moreover, software manages complex networks in addition to managing individual platforms. Because of the increasing complexity of hardware and its ever-increasing role in complex systems, developing software is now an integrated and comprehensive part of systems development. Thus, systems engineering must include software engineering as an integral discipline, not just another design engineering effort to implement functionality. Next, we'll talk about the nature of software development, and we'll think about the types of software. While many people have presented categories of software over the past decades, we find that the most of them can be consolidated into three broad types. First of all, system software. This category of software provides services for other software and is not intended for standalone use. The classic example of this is the operating system. The operating system of a computer or server provides multiple data, file, communication, and interface services, among others, for other resident software. Another category is embedded software. This category of software provides specific services, functions, or features of a larger system. This type is most readily recognized with system engineering, since a basic principle allocated functionality to specific subsystems includes software-based subsystems. So examples of this type are rarely found in systems such as satellites, defense systems, homeland security systems, healthcare, and energy systems. Then there's application software. This category of software provides services to solve a specific need and is considered standalone. Applications typically interact with systems and embedded software to utilize their services. Examples include those of our commercial software, including the popular office productivity applications, word processors, spreadsheets, and presentation support. So let's get into software types. Although these three categories cover the wide variety of software today, they do not provide any understanding of the multiple specialties that exist. And so in this table, we provide an additional characterization. The three major software categories are shown in the table for comparison. For additional categories are presented: engineering / scientific, product line, web-based, and artificial intelligence. While all four fall under one or more of the three major categories, each type also addresses particular niches in the software community. So we can see a larger set of categories by looking at that chart. Next, we'll talk about types of software systems and explore software-dominated systems. While software has become a major element in virtually all modern complex systems, the task of system engineering a new system may be very different depending on the nature of functions performed by the software system elements. Despite the fact that there are no commonly accepted categories for different types of systems, it is useful to distinguish three types of software systems, which will be referred to as software embedded systems, software intensive systems, and computer intensive systems. The term software dominated systems will be used as inclusives of the software systems in general. So the characteristics of three categories of software dominated systems and familiar examples are listed in this table, and we'll be getting into more detail in the next slides as we continue to be thinking about this topic. So let's get into the details of the nature of software development. We'll be looking at software embedded systems, software intensive systems, and data intensive computing systems, which I just briefly mentioned when we were using the previous slide to help us with this material. So software embedded systems, the software embedded systems, also referred to as software shaped systems, real-time systems, or social technical systems, are a hybrid combination of hardware, software, and people. This category of systems is one of which the principal actions are performed by hardware, but the software playing a major supporting role. Examples are vehicles, radar systems, computer-controlled manufacturing machinery, and so on. The function of software is usually that of performing critical control functions in support of human operators and the active hardware components. Software embedded systems usually run continuously, typically on embedded microprocessors, and the software must therefore operate in real time. In these systems, software is usually embodied in components designed in accordance with requirements flowing down from system and subsystem levels. The requirements may be specified for individual software components or for a group of components operating as a subsystem. In these systems, the role of software can range from control functions in household appliances to highly complex automation functions in military weapon systems. Next, we have software-intensive systems. Software-intensive systems, which include all information systems, are composed largely of networks of computers and users in which the software and computers perform virtually all the system functionality, usually in support of the human operators. Examples include automated information processing systems such as airline reservation systems, distributed merchandising systems, financial management systems, and so on. These software-intensive systems usually run intermittently in response to user inputs and do not have as stringent requirements on latency as real-time systems. On the other hand, the software is subject to system-level requirements directly linked to user needs. These systems can be very large, as well as being distributed over extended networks. The World Wide Web is an extreme example of a software-intensive system. Software-intensive systems, software is key at all levels, including the system control itself. Hence, there must be system engineering from the beginning. Most of them can be thought of as transactional systems, say with financial, airline reservation, command, and control. They are generally built around databases that contain domain information entities that must be accessed to produce the desired transaction. Finally, we have data-intensive computing systems, a type of software system that is significantly different from the above software type categories includes large-scale computing resources dedicated to executing complex computational tasks. Examples are weather analysis and prediction centers, nuclear effects prediction systems, advanced information decryption systems, and other computationally intensive operations. These data-intensive computing systems usually operate as facilities in which the computing is typically performed either on supercomputers or on assemblies of high-speed processors. Some cases, the processing is done by a group of parallel processors with computer programs designed for parallel operators. The development of data-intensive computing systems requires a systems approach like other systems. However, most of these are one of a kind and involve very specialized technical approaches. Accordingly, what we're covering in this chapter will be focused on the system engineering problems associated with the much more common software embedded and software intensive systems. Well, let's start out briefly by talking about the hardware and software differences, and then we'll use the next slide to focus on the details. So it was noted at the beginning of this chapter that there are differences between fundamentally between hardware and software, and that that have profound effects on the system engineering of software-dominated system. Every system engineer must have a clear appreciations for these differences and their import. And so what this table is trying to show, it's devoted to describing the software systems and how they differ significantly from hardware. So you may want to spend some more time going over that and thinking about it. But I'll give a sense of going over each one of these things and to highlight some more details about the differences. And you can also just refer to the other text that I have here. So let's first of all start with the nature of software development and the differences by first of all thinking about the structural units. Most hardware components are made up of a standard physical parts such as gears, transistors, motors, and so on. The great majority are implementations of commonly occurring functional elements such as generate torque or process data. In contrast, software structural units can be combined in countless different ways to form the instructions that define the functions to be performed by the software. There's not a finite set of commonly occurring functional building blocks, such as make-up hardware, subsystems, and components. The main exceptions are generic library functions, say trigonometric, contained in some software programming environments, and certain commercial software components, mostly related to graphical user interfaces or GUIs, the functions that they serve. Next, we have interfaces. Because of the lack of well-defined physical components, software tends to have many more interfaces with deeper and less visible interconnections than hardware systems. These features make it more difficult to achieve good system modularity and to control the effects of local changes. Next, we have functionality. There are no inherent limits on the functionality of software as there are on hardware due to the physical constraints. For this reason, the most critical, complex, and non-standard operations and systems are usually allocated to software. Then we have size. While the size of hardware components is limited by volume, weight, and other constraints, there is no inherent limit to the size of a computer program, especially with modern memory technology. The large size of many software-based systems constitutes a major system engineering challenge because they can embody an enormous amount of custom-built system complexity. Then we have changeability. Compared to the effort required to make a change in a hardware element, it is often falsely perceived to be easy to make changes in software. That is, quote, merely by altering a few lines of code. The impact of software changes are more difficult to predict or determine due to the complexity and interface problems cited above. A, quote, simple software change may require retesting of the entire system. Then we have failure modes. Hardware is continuous in both structure and operation, while software is digital and discontinuous. Hardware usually yields before it fails and tends to fail in a limited area. Software tends to fail abruptly, frequently resulting in system breakdown. And finally, we have abstraction. Hardware components are described by mechanical drawings, circuit diagrams, block diagrams, and other representations that are models of physical elements readily understood by engineers. Software is inherently abstract because the actual code, architectural, and modeling diagrams are highly abstract, and each diagram restricted in its information context. Abstractions may be the single most fundamental difference between software and hardware. So the above differences that are summarized in the table that I was showing on the previous slide profoundly affect the system engineering of complex software-dominated system. Not appreciating these differences and effectively accounting for them can contribute to spectacular failures in major programs. For the majority of system engineers who do not have experience in software engineering, it is essential that they acquire a grounding in the fundamentals of this discipline. And so the following sections are intended to provide a brief overview of software and the software development process. So we're getting a crash course in software engineering in the midst of our software engineering class. Well, next we'll discuss software development lifecycle models, and we'll go through each one of these here, but let's give some perspective first on this before we get into those details. So as described in other chapters, and we refer to chapter 3 here as an example, every development project passes through a series of phases as it evolves from inception to its completion. The concept of a life cycle model is a valuable management tool for planning activities, staffing, organization, resources, schedules, and other support activities required for a project's successful execution. It is also useful for establishing milestones and decision points to help keep the project on schedule and budget. The system lifecycle model consists of developing, producing, and fielding a typical new large-scale complex system. It was seen to consist of a series of steps beginning with the establishment of a bona fide need for a new system and systematically progressing to devising a technical approach for meeting the needs, engineering a hardware and software system embodying an effective, reliable, and affordable implementation of the system concept, validating its performance, and producing as many units as required for distribution to the users and customers. The software elements in software embedded systems perform critical functions, which are embodied in components or subcomponents. Therefore, the system lifecycle is governed by the nature of the system and major subsystems and generally follows the steps of characteristic of a system. A significant feature of the lifecycle of software embedded system is the fact that there is no production for the software elements themselves. only of the processors on which the software runs. Also, there is cause for caution in that software elements are deceptively complex for their size and usually play critical roles in system operations. Hence, special measures for risk reduction is in this area needs to be considered. So what are the basic development phases? We'll talk about that. And so just as the system engineering method consists of 4 basic steps of requirement analysis, functional definition, physical definition, and design validation, then software development process can be resolved into 4 basic steps. First, there's analysis. Second, there's design, including architectural, procedural, etc. 3, there's coding and unit testing, also called implementation. And finally, 4th, test, including integration and system tests. Although not strictly coincident with the system engineering method, the general objectives of each of these steps closely correspond. It should be noted that, like the system engineering method, different versions of software process use variation in terminology in naming the steps or phases, and some split up one or more of the basic steps. For example, design may be divided into preliminary design and detailed design. Unit test is sometimes combined with coding or made a separate step. System test is sometimes referred to as an integration and test. It must be remembered that this stepwise formulation is a model of the process and hence subject to variation and interpretation. For the categories of software-intensive systems, which dominate communication, finance, commerce, entertainment, and other users of information, there are a variety of lifecycle models in use. A few notable examples of these are discussed briefly in just a moment. As in the case of system lifecycle models, the various software process models involve the same basic function, differing mainly in the manner in which the steps are carried out, the sequence of the activities, and in some cases, the form in which they are represented. Overall, software development generally falls into 4 categories. First, linear. Like formal system development lifecycle models, the linear software development model category consists of a sequence of steps, typically with feedback resulting in software product. Linear development models work well in environments with well understood and stable requirements, reasonable schedules and resources, and well-documented practices. Next, we have incremental. Incremental models utilize the same basic steps as a linear model, but repeat the process in multiple iterations. In addition, not every step is performed to the same degree of detail within each iteration. These types of development models provide partial functionality at incremental points in time as the system is developed. They work well in environments with stable requirements where partial functionality is desired before the full system is developed. Next, we have evolutionary. Evolutionary models are similar to the incremental concept, but work well in environments where the final product's characteristics and attributes are not known at the beginning of the development process. Evolutionary models provide limited functionality in non-production forms for experimentation, demonstration, and familiarization. Fallback is critical to evolutionary models as the system evolves to meet the needs of the user through these 3 procedures. Finally, we have agile, and agile development models deviate most from the 4 basic steps we have identified above. With linear, incremental, and evolutionary models, the 4 steps are manipulated into different sequences and repeated in different ways. While agile development environments, the 4 steps are combined in some manner and the delineation between them are lost. Agile methods are appropriate for environments where structure and definition are not available, and change is the constant throughout the process. In addition to the 4 basic development model categories above, specialized development models have been proffered, practiced, and published. The well-known examples are the component-based development model and the aspect-oriented development model. These special purpose models have specific but limited application warranting their use. We have chosen to omit these specialized model from this discussion that we're having here. Okay, well, we'll start talking in more detail about these models, and we'll get into the software development waterfall cycle that we're showing here. So let's talk in general first. Linear development models. The waterfall model is the classic software development lifecycle model, also called the sequential model, and we're showing that in this figure. It consists of the sequence of steps systematically proceeding from analysis to design, coding and unit test, and integration and system test. The waterfall model with feedback depicts the adjustment of inputs from a preceding step to resolving unexpected problems before proceeding to the subsequent step. The waterfall model corresponds most closely to the conventional system lifecycle. So here in this table, we're thinking about system engineering in the waterfall model. It lists the system lifecycle phases, their objectives, and the corresponding activity in the waterfall lifecycle phase. Over the years, the basic waterfall model has morphed into many variations, including some that quite honestly could no longer be described as linear. Waterfall has been combined with the other types to form hybrids that could be classified as a combination of the two or more categories. And while the basic waterfall model is rarely used in today's modern software engineering community, its basic principles can be recognized throughout, as will be evidenced in some of the things we'll be talking about as we progress in this lecture. Okay, let's talk a little bit about the software incremental model. And so the basic incremental model involves two concepts. One, performing the basic steps of software development repeatedly to build multiple increments. And two, achieve partial operational functionality early in the process and build that functionality over time. So the figure we're showing depicts this process using the steps of the basic waterfall process model. Not all steps of every increment are performed to the same level of detail. So the analysis phase may not need the same attention in the second and third increments as it received in the first increment. Initial analysis may cover the needs requirement and feature definition for all increments, not just the first. Similarly, by the second iteration, the overall design of the software system may be largely completed. Further design would be needed in the third iteration. Another aspect of incremental development concerns the incremental releases, sometimes called builds. As a new increment is released, older increments may be retired. In the purest form, once the last increment is released, all increments are retired. Of course, situations arise when customers are fully satisfied with an increment, leading to multiple increments, and thus versions of the software or future increments are canceled. So this is depicted here in the figure with the triangles. We see a couple of different increments that are still being out there that are utilized by the customer base. And another thing that we have that's out there is the rapid application development RAD model, sometimes called the all-at-once model, features an incremental development process with a very short cycle time. It is an iterative form of the waterfall model, depending on the use of previously developed or commercially available components. Its use is best suited to business applications, software, or limited size that lend itself to relatively quick and low risk development, and whose marketability depends on deployment ahead of an anticipated competitor. Next, we'll talk about the evolutionary development model, or you could think of it as a spiral model here. So this would be something that would be useful at times. In a situation where user needs and requirements are not well defined, and or development complexity is sufficiently high to incur significant risk, an evolutionary approach may be best. The basic concept involves the development of an early software prototype, a software product or prototype. The prototype is not intended for actual operation, sales, or deployment, but to assist in identifying and refining requirements or by reducing development risk. The purpose of the prototype is identifying and refining requirements. Then typically an experimental version of the system or a representative portion that exhibits the characteristics of the user interface is built early in the design phase of the development and operated by the intended user or a surrogate of the projected user. With the flexibility of software such as prototype can often be designed and built relatively quickly and inexpensively. Attention to formal methods, documentation, and quality design need not be implemented since the version is not intended for production. In addition to refining the requirements by building trial user interfaces, software prototyping is often used as a general risk reduction mechanism as in the advanced development phases. New design constructs can be prototyped early to refine the approach. Interfaces with other hardware and software can also be developed and tested early to reduce risk. It's often necessary to discover the real requirements of the system interfaces by testing preliminary models of the system in the field. And so the most common form of the evolutionary model is a spiral model, and that's what we're showing in this figure. It depicts a version of the spiral development model. It differs in form by starting in the center and spiraling outward. The expanding spirals represent successive prototypes, which iteratively perfect the attainment of customer objectives by the system. Finally, the finishing steps are applied on the last spiral/prototype, resulting in a finished product. While all evolutionary, with all evolutionary method, it's important to plan for the disposition of the prototypes or spirals after they have been used. Examples abound where a spiral approach was adopted and one or two prototypes were developed and tested using actual user or surrogates. However, after experiencing the prototype, the customer declared the product sufficient and requested immediate delivery. Unfortunately, without formal procedures and methods in place, nor general quality assurance followed in the prototype development, the final product, quote, was in no condition to be deployed in the field or sold to the market as well. Upon deployment, problems ensued quickly. Our recommendation is that prototypes should be discarded upon completion of their purpose, and the customer should be forewarned of the significant risk involved in deployment prototypes as operational systems. Okay, next we'll talk about the concurrent development model, and also we'll give an overview perspective of agile methods. So the second model, which falls under the evolutionary category, is called the concurrent development model. This approach eliminates the two concepts of sequence and increments and develops all phases simultaneously. The model achieves this approach through the definition of software development states. Software models are tagged with which state they belong. Formal state transition criteria are defined that enable software modules to transition from one state to another. Development teams focus on specific activities within a single state. So what we're showing here in the figure depicts an example state transition diagram associated with this type of a model. So software models are initially assigned to the waiting development state. This state could be thought of as a queue for the development team. A model is not transitioned to the quote under development state until a team is assigned to its development. Once completed, the model is transitioned to the quote under review state, where a review team or person is assigned. Again, transition does not occur until a team is assigned to the module. This process is repeated. Since models are developed simultaneously by different teams, models can be in the same state. A push-pull system can be implemented to increase efficiency of the associated teams. Well, let's have a discussion about agile development methods. A common result of many software development projects is failure to adapt to changing or poorly defined user requirements and a consequent impact on project costs. Response to this situation was a formulation of an adaptive software method referred to as, quote, agile. It uses an iterative life cycle to quickly produce prototypes that the user can evaluate and use to refine requirements. It is especially suitable for small to medium-sized projects, say with less than 30 to 50 people, where the requirements are not firmly defined and where the customer is willing to work with the developer to achieve a successful product. So this last point is particularly important. The agile methodology depends on customer and user involvement. Without a commitment from the customer for the level of interaction, the agile methodology occurs in significant risk. As defined by its proponents, the agile methodology is based on the following postulates, assuming the above conditions. So requirements are not wholly predictable and will change during the development period. This is especially true in software development. Corollary is the customer priorities are likely to change during the same period. 2, design and construction should be integrated because the validity of the design can seldom be judged before the implementation is tested. 3, analysis, design, construction, and testing are not predictable and cannot be planned with adequate levels of precision. There is a feeling that the software is easily changed, so throughout development, software requirements are prone to frequent changes. These methods rely heavily on software development teams to conduct simultaneous activities. Formal requirements analysis and design are not separate steps. They are incorporated into the coding and testing of software. This concept is not for the faint of heart customer. A great level of trust is required. Nevertheless, agile methods represent a leap in software development that can lead to highly robust software more quickly than traditional methods. Agile methods include a number of recent process models, and we'll go through these one at a time. First, the adaptive software development, ASD. It focuses on successive iterations of 3 activities: speculation, collaboration, and learning. The initial phase, speculation, focuses on customers' needs and missions. The second phase, collaboration, utilizes the concept of synergistic talents working together to develop the software. The final phase, learning, provides feedback to the team, the customer, and the other stakeholders, and includes formal review and testing. Next, there's extreme programming, or XP. It focuses on successive iterations on 4 activities: planning, design, coding, and testing. Requirements are identified through the use of user stories, which are informal user descriptions of features and functionality. These stories are organized and used through the iterative process, including as the basis for final testing. Then we have Scrum. Scrum focuses on a short 30-day iterative cycle with strong teaming. The process yields several iterations in various maturities with which to learn, adapt, and evolve. With each cycle, a basic set of activities occurs: requirements, analysis, design, evolution, and feature. Next, we have feature-driven development. It focuses on short iterations, say about 2 weeks, each of which delivers tangible functionality, that is, features that the user values. Eventually, features are organized and grouped into modules that are then integrated in the system. Finally, there's the Crystal family of agile methods, which focuses on adaptation of the core set of agile methodologies to individual projects. In all of the above approaches, quality and robustness are required attributes of products. Thus, the iterations are to be built on rather than thrown away. All projects that are based on uncertain requirements should consider the above principle in deciding on methodology to be used. In terms of software system upgrades, because of the rapid evolution of information technology, the associated development in data processors, peripherals, and networks, and the perceived ease of introducing software changes, there are relatively frequent cases where system software is subjected to significant modification or upgrades. In a large fraction of instances, the upgrades are planned and implemented by different individuals from those responsible for the development, with the resulting probability of inadvertent interface or performance deficiencies. Such cases call for participation of and control by system engineering staff who can plan the upgrade design from a systems point of view and ensure an adequate requirement analysis, interface identifications, application of module principles, and thorough testing at all levels. When the system to be upgraded was designed before the general use of modern programming languages, there can be severe problems of dealing with obsolete language no longer supported by modern data processors. Such legacy software is generally not capable of being run on modern high-performance processors, and the programs, which total billions of lines of code, have to either be rewritten or translated into a modern language. The cost of the former is in many cases prohibitive, and the latter has not come into general practice. The result has been that many of these systems continue to use obsolete hardware and software and are maintained by a dwindling group of programmers still capable of dealing with the obsolete technology. Well, let's talk about the software content development, and we'll be focusing on the analysis and design at the moment. And so the analysis and design steps in the traditional software lifecycle described in the previous section generally correspond to the concept development stage. These are the activities that define the requirements and architecture of the software elements of the system. The line of demarcation between analysis and design may vary substantially among project and practitioners. There being broad areas referred to as design analysis or design modeling. For this reason, the subsections that we're going to be talking about next will focus more on approaches and problems that are of special interest to system engineers than on issues of terminology. So let's focus on, I've kind of put these subheaders from the text here in the bottom. So first of all, needs analysis. The precondition for the development of any new system is that it is truly needed, that a feasible development approach is available, and that the system is worth the effort to develop and produce it. In the majority of software-intensive systems, the main role of software is to automate functions in legacy systems that have been performed by people or hardware, to do them at less cost and less time and more accurately. The issue of need becomes one of trading off the projected gains in performance and cost against the effort to develop and deploy the new system. In new systems in which key operations performed by people or hardware are to be replaced with software, users are typically not unanimous regarding the needs, and the optimum degree of automation is seldom determinable without building and testing. Further, an extensive market analysis is usually necessary to gauge the acceptance of an automated system and the cost and training that this entails. Such an analysis also usually involves issues of market penetration, customer psychology, introduction trials, and corporate investment strategies. And a part of this, in terms of the needs analysis, is to think about the feasibility analysis. The decision to proceed with system design has to be seen to require the demonstration of technical feasibility. Within the realm of software, almost anything appears feasible. Modern microprocessors and memory chips can accommodate large software systems. There's no clear size, endurance, or accuracy limits as such are on hardware components. Thus, technical feasibility tends to be taken for granted. This is a great advantage of software, but also invites complexity in the assumption of challenging requirements. However, the resulting complexities may in itself prove too difficult and costly. Then we have to be thinking about software requirement analysis. The scope of the requirements analysis effort for a new system usually depends on whether the software is an element in a software embedded system or it embraces a total software intensive system. In either case, however, the development of a concept of operation should play an important part. And relatedly, we want to be thinking about the software embedded system components. So as noted before, the software elements in software embedded systems are usually at the component level, referred to as the computer system configuration item, CSCI. The requirements are generally at the system and subsystem levels and are allocated to CSCIs, usually in a formal requirement specification document. The document team is expected to design and build a product to these specifications. Too often, such specifications are generated by system engineers with an inadequate knowledge of software capabilities and limitations. For example, a large dynamic range in combination with high precision may be prescribed that may unduly stress the system computational speed. Other requirement mismatches may result from the communication gap that frequently exists between systems and software engineers and organizations. For such reasons, it is incumbent on the software development team to make a thorough analysis of requirements allocated to software. These reasons also constitute a good argument for including software engineers in the top-level requirements analysis process.